Hello everyone and welcome back to the channel for linked list the whiteboard deep dive. If you're looking to understand memory pointers and the true cost of flexibility in data structures, you have come to the right place. Before we jump in, I want to quickly tell you about our companion site bitbytoken.com, which I am showing up here. If you look here, this site is a companion site to our various articles that we try to post in CSAITTL. This is actually broken by down to like different sections, which are core software engineering, data engineering, machine learning, or AI engineering. For each of these components, we have sections where you can look for fundamentals, which includes database, event-driven, for example, for core software engineering, and then correspondingly we have the example solutions as well. So, for example, you can look at different example for system designs here. For example, in this one is a pretty detailed one. You can actually take a look at it through like it has functional requirement, non-functional requirement. We look at data model as well, which will cover all these details. Then if you want to look at different sequence diagrams, we are covering those as well. All in all, pretty much detailed diagram that we have here. We provide as much details as possible. Do check it out and provide us your reviews on the comments. Let us know how we can make it more beneficial, more better. Um, okay, now let's jump back into the actual article of the day today. Uh, Please remember to like, share, and subscribe to the channel for more content like this. Today, we are going to unravel the intricacies of linked lists, moving beyond the straight lines to understand how these dynamic structures work under the hood. Let's begin by contrasting the array with the linked list to highlight their fundamental differences. On the left, the array is like a fixed capacity bookshelf. You have number slot and you can easily access any item, like item 10 directly. But if you have a new item and shelf is full, you're stuck. It has fixed capacity and no space. You'd have to have a completely new, larger bookshelf and move everything over. On the right, the linked list is dynamic. Imagine a chain of people, each holding a piece of data and pointing to the next person. If you want to add a new item, you simply introduce a new person into the chain and just point to the next one. This dynamic nature gives linked lists immense flexibility that arrays lack. At the heart of every linked list is the atomic unit, the node. A node fundamentally holds two things. First, we have the data, which is the cargo, or the actual value that you care about storing, whether it's a number, a string, or an object. Second, we have the next pointer, which is the coupling, which is this is the address or reference to what comes next in the sequence. The simple two-part structure is how all nodes are connected to form the linked list. Now, for the reality, the non-contiguous memory. Unlike arrays, which occupy a contiguous block of memory, the nodes of a linked list are typically scattered across the heap in system RAM. As you can see from the winding blue line, node A, node C, node B, and node D are all in different non-adjacent memory locations. The next pointers are what connect these scattered pieces. Node A points to C, C points to B, B points to D, and finally D points to null, signifying the end of the list. This non-contiguous allocation is what gives linked lists their flexibility, but also introduces certain performance characteristics. This brings us to the linear search problem, leading to excess time of ON. In a linked list, there's a crucial caveat no teleporting. To get to, say, node 99, you must start from the beginning and sequentially visit 98 other nodes before it. You literally have to follow the pointers one by one, like walking a path. Unlike arrays, where you can instantly jump to an index, linked lists require this linear traversal. This means that accessing a specific element takes time proportional to the position in the list, making it an ON operation in the worst case. Now, let's look at the superpower, the head insertion. This is where linked lists truly shine, offering a complexity of O1. This means insertion at the beginning of the list happens in constant time. Regardless of the list size, there's no shifting, just swapping pointers. As you can see, to insert a whip new data node at the head, First, new tap with new data nodes. Next pointer is made to the point to the current head, which is node A. Then the head pointer itself is updated to point to the WIP new data node. This elegant process involves only a few pointer reassignments, making it incredibly efficient. While head insertion is O1, insertion in the middle is a bit more nuanced. It involves two steps. Step 1, the commute, or finding the insertion point, which can take O(n) time. As shown, to insert a new node after node 4, you must traverse the head all the way to node 4. Only after finding the correct spot can you proceed to step 2, which is the wiring, which is the actual insertion in O1 operation. Here, the WIP new data node is connected between nodes 4 and 5. So, while the wiring is fast, the arrival to correct location can be slow, making the overall operation fast insertion, slow arrival. To optimize specific operation, we can use the tail pointer optimization. Appending a new node to the end of a linked list without a tail pointer would require traversing the entire list, resulting in an ON, walk the whole list complexity. This is inefficient. However, by maintaining a tail pointer that always points to the last node, appending with tail becomes an O1 instant access operation. You simply connect the new node to what the tail node currently points to, and then you update the tail to the new node. This significantly speeds up addition to the end of the list. Now, a crucial caveat: deletion requires the predecessor. To delete a node, say node B, in a singly linked list, you cannot just point B and delete it. Instead, you must modify A, its predecessor. You need to make node A's next pointer bypass B and point directly to C. This effectively bridges the gap and removes B from the chain. This means that to delete a node, you must either already have a reference to its predecessor or you'll have to traverse the list to find it, which can add to the deletion cost. To overcome some of the limitation of singly linked list, we introduce doubly linked list. These offer several key advantages. The first is bidirectional travel, as each node now includes a prep pointer that points to the previous node. In addition to the data and the next pointers, this allows you to move forward and backward. The second benefit is over deletion if you have the node. Because the node knows its predecessor, deletion can be performed instantly. The trade-off is that it, it uses more memory, which because of two pointers per node, increasing the memory footprint of the structure. Another important variation is a circular list. These are characterized by the infinite loop. No null terminator. In a circular list, the last node next pointer points back to the first node, creating a continuous cycle A to B to C to D to E to F, and then F back to A. These are the great for round robin scheduling and continuous processes like playlist. However, they are dangerous for while loops if not handled carefully, as standard loops that check for null terminator will run forever, leading to infinite loops. Let's address a critical caveat, the hidden cost, which is our memory overhead. While big O complexity often focuses on time, memory usage is a significant factor. Looking at 1 million integers, an array is the most memory efficient using approximately 8 MB. A singly LL for the same data incurs a pointer overhead, bringing its total memory to approximately 32 MB. A WLL, doubly linked list, uses even more, around 40 MB, due to having two pointers per node. This clearly illustrates that while linked lists offer flexibility, they come with a substantial memory cost, especially for small data types that where the pointer size can dwarf the data size. Now for the big O showdown. A cheat sheet comparing array, singly linked list, and doubly linked list performance for access of particular index. For accessing any particular index, arrays are the clear winner at O1. Linked list, both singly and doubly, are ON. Insert head is ON for arrays due to shifting, but O1 for both type of linked list. Insert tail can be O1 for arrays, which is the amortized value, and O1 for linked list if a tail pointer is used. Delete in the middle is ON for arrays and singly linked list. but an optimized one for doubly linked list if you have the known node reference. In summary, arrays win at access, linked lists win at restructuring. For your interview survival kit, here are the two key patterns for linked list. First, the dummy head. This is a placeholder node placed before the actual head of the list. It simplifies edge cases by ensuring that head is never null, making insertion and deletion logic at the very beginning of the list much cleaner. Second, the tortoise and the hare for faster slow pointers technique. This involves one pointer moving slowly and another pointer moving fast. It's invaluable for cycle detection and finding middle in linked list as demonstrated by the looping diagram. My final advice for mastering linked list is simple. Think in pointers, not indexes. Unlike arrays where you work with numerical position, linked lists are all about the connections. As the visual suggests, understanding how to cut and tie these connections is paramount. If you can visually draw the arrows and how they change during operations, you can write the code. This visualization is the key to correctly implementing linked list algorithms and avoiding common bugs. Thank you for joining me on this deep dive. What are your biggest takeaway from understanding linked list? Share your thoughts in the comments below. And please do not forget to like, share, and subscribe to the channel for more programming insights. And be sure to check out bitbytoken.com for even more resources. Happy coding!